Where our statistics class begins is with variables and data. Really, I like to tell students that this first unit is going to feel more like a social studies class. There will be some math involved, but the math is going to get much more complicated as we move on to future units. The first unit is more about terminology, understanding the gathering of data, and other things that aren't as mathematically inclined. There will still be math in it, but I promise you that it's going to get worse as we go on. You definitely don't want to get a false sense of security if it feels like these first two lessons are a breeze. That said, we're going to begin with understanding some terminology and how to design experiments. In general, I don't need you to write down exact definitions in your notes. I want you to understand in context what these words mean, but I'm not going to give you a homework or a test problem where it says, what's the definition of this? It might be asked for you to choose between multiple choice explaining some further part of a question where this terminology is involved, but it's more about you understanding the words in context than it is you being able to spit back a definition. So the words we're learning here are experimental unit. An experimental unit is the individual or object on which a variable is measured. A single measurement or data value results when a variable is actually measured on an experimental unit. So the experimental unit is where we get one piece of data from. If I'm going to ask 25 students what their heights are to try and estimate the average height of a student, in that case my experimental unit is one student, because each of them is giving me their height, the variable I care about, but it's coming from that experimental unit, the student. A population is the set of all measurements of interest to the investigator. It depends what I want. If I set out to say what's the average height of a student currently enrolled at Manor College, in that case there would be 400 students or so currently enrolled. It's possible that I could go around and measure every student and get the entire population and know the true number. What's the average height of a Manor student? If instead I said what's the average height of a college student in America, that would be a lot tougher. A lot more than 400 people. I'd have to round up, measure, take an average, find what that height is. That said, the number exists. So the idea of statistics is we want to try and get that number best we can without having to actually measure all whatever untold million college students there are in America. In order to do that, we're going to take a sample. A sample is a subset of measurements selected from the population of interest. So if I randomly selected 25 students of mine, those could be a sample for Manor College, they could be a sample for all college students, they could be a sample for all people in the world, depending upon what I'm looking for. As long as I'm using the right methods to get that sample, the sample could be reflective of the population that I'm looking for. But the key things I need you to take away from this slide: experimental unit, where I get one piece of data; population, everybody I would want to study if I could. Usually it's not feasible to study everyone because the group is too large, so instead we take a sample, which is a smaller part of that population of interest. I'm going to ask you to look at examples like this and pull out the experimental unit, the variable of interest, the population of interest, and the sample. So here we have a situation: the math department at Manor College is interested in what portion of their incoming students completed a geometry course in high school. They asked 50 incoming students and find that 68% of them completed a geometry course in high school. What's the experimental unit? What's the variable of interest? What's the population of interest? And what's the sample table? So we're going to start with what's the experimental unit. In this case, one student would be the experimental unit. That's where we get the piece of information. We ask each of the students, and each one of them tells us either yes, they completed geometry, or no, they did not complete geometry in high school. For what's the variable of interest, that is my variable. Did you complete geometry in high school? Completion of geometry might be a way to phrase it as a variable. I'm not really as concerned with how you're phrasing it, more that you're identifying what they're really looking for. What's the population of interest? So to find the population, it's usually best to look back at the start of the problem, where the researcher explained what they were looking for. The math department at Manor College is interested in what portion of their incoming students completed a geometry course in high school. So who they care about is the incoming students to Manor College. They don't care about some larger group of all college students. They specifically are concerned with the ones that are attending Manor. So the population of interest, I'd want to have all those words in it. Incoming students to Manor College. What's the sample taken? That's the smaller group of students. In this case, 50 incoming students would be the sample. So the answers are here for you if you want to look over it. As always, this PowerPoint is posted to Canvas, so you can click on it through it on your own. But basically, every time that I ask you a question, I'm going to put the answers up here. I'm going to click through these slides rather quickly when I'm going over them in lecture because I'm going to try and go over the answers before. Example situation 2. The facilities department is interested in what % of college classrooms are equipped with smartboards. They randomly walk into 5 rooms at each of 20 local colleges and find that 87% of the rooms are equipped with smartboards. So, in this case, the experimental unit, instead of being one student, is one room. Each room either yes has a smartboard or no does not have a smartboard. So the variable of interest is has a smartboard, does not have a smartboard. What's the population of interest? So in this case, the facilities department is interested in what % of college classrooms. They don't care about whether the colleges are in PA, they don't care about whether the college is of a certain size. All they say is college classrooms. So in this case, the population would be all college classrooms. What's the sample taken? So here they say they randomly walked into 5 rooms at each of 20 local colleges. 5 rooms, 20 colleges is really 100 total rooms that they're walking into. So the sample, I could phrase it as 5 rooms in each of 20 colleges, or I could say the 100 rooms they walked into. So here this goes over those answers again. 1 room, is there a smartboard? All college classrooms. And 100 classrooms, 5 in each of the 20 colleges. Example situation 3. The math department at Manor College wants to determine what portion of the 2020 graduating class is employed 1 year after completing the certificate program at Manor. They call 115 2020 graduates and find that 91% of them are currently employed. What's the experimental unit? In this case, we're getting one piece of information from one Manor graduate. So one graduate would be the experimental unit. The variable of interest is, are you employed? Employed or not employed? What's the population of interest? So we want everybody in the 2020 graduating class. What's the sample taken? Here we called 115 of the 2020 graduates. So the 115 graduates that we called are the sample. Oh, I'm sorry. It looks like this answer, I changed things slightly. So the slide before said 115, this slide says 55. I apologize, I have to fix that. But really, this 55 graduates is just because of that change that I should have made in the slide before. All those answers are still valid. The vet tech department at Manor College is trying to estimate how much food a horse consumes in a week. They keep track of 10 horses under their care and find that they eat on average 27 pounds of food a week. What's the experimental unit? Take a minute, think about it for yourself, and then I'm going to give you an answer. So here, the experimental unit is 1 horse. Next question, what's the variable of interest? In this case, the variable of interest is pounds of food eaten per week. For each of the horses, we're going to find out how many pounds of food they ate in the past week. What's the population of interest? So take a minute, look and see if you can identify who are they trying to study. In this case, it just says they're trying to estimate how much food a horse consumes in a week. So the population is not limited to any particular type of horse. It's all horses that they care about. What's the sample taken? The sample taken is the 10 horses under their care. So again, here are those answers. That concludes the first part of what we're doing today, which is understanding what an experimental unit is, what a variable of interest is, what a population is, and what a sample is. The next thing we'll be looking at today is how to classify different types of data. So there's 2 distinct ways that we can first classify a piece of data. Specifically, Is it a qualitative variable or is it a quantitative variable? If it's a qualitative variable, it measures a quality or characteristic on each experimental unit. If it's a quantitative variable, it measures a numerical quality or amount on each experimental unit. That doesn't really give you a clear picture of how to choose which is which. Basically, the distinction is, if it's a qualitative variable, I can just put it into a category that it belongs into. I can say that if we're looking at the color of shirt that somebody came into class, this person is wearing a red shirt, that person is wearing a blue shirt, I put this person in the red bin, I put that person in the blue bin. I can say where they belong, I can't really make comparisons between them. As opposed to if we look at one of the quantitative variables, if we look at shoe size, for instance. If I went around the room and asked everybody their shoe size, I could line everybody up on a naturally occurring numerical scale. I could say these people have size 11 shoes, these people have size 12 shoes, these people have size 10 shoes. Comparisons between them would make sense. 11 is 1 more than 10, 11 is 1 less than 12. So there has to be a naturally occurring underlying numerical scale that I can make comparisons between for something to be a quantitative variable. It can only fit into a certain category for it to be a qualitative variable. Normally these are somewhat straightforward, but there's definitely a few tricky ones. We're going to see some of that as we look at some examples. So what I want you to do is take a minute here, basically going to count to about 10 or 20 in my head. I want you to go through each of these and decide whether you think it's going to be a qualitative variable or a quantitative variable. So weights of babies, baby names, hours in labor, price of balloons at the gift shop, hospital zip code, number of babies the doctor has delivered, type of medical insurance, and cost of hospital stay. So we're going to begin with the weights of babies. If this baby weighed 10 pounds 6 ounces, this baby weighed 10 pounds 4 ounces, I know where they go on a natural scale, I know what the difference is between them. For that reason, the weights of babies would be a quantitative variable. Baby names, this baby's named John, that baby's named Jack. I guess you could put them in alphabetical order, but really that's not a numerical scale as much. This is just a case where I can say all these babies were named John, all these babies were named Jack, and put people into the names that they were given. For that reason, it's a qualitative variable. Hours in labor. This mom was in labor for 14 hours, that mom was in labor for 16 hours. Again, I can make comparisons, I can lay them out in an exact numerical order. For that reason, hours in labor is a quantitative variable. Similarly, the price of balloons at the gift shop, this balloon costs $4.95, that balloon costs $2.95. I can line up and say, here's the order of prices. So that would also be a quantitative variable. Hospital zip code is the trick on this page. Hospital zip codes are numbers. You want it to be a quantitative variable because it's really easy to think in your head. If it has numbers, it's quantitative. If it doesn't have numbers, it's qualitative. But tricks like this are the reason that we can't do that. There's really no natural scale for zip codes. I know they're all 5 numbers. At one point, they moved from east to west in the country, but now there's so many new zip codes that have gotten put in that they don't really make sense next to each other. It's not like I know that if I live in 19454, that's 10 miles east of 19444. It's something where really all they do is act as identifiers. They put you in a box. If you live in 19454, then you are with these other 10,000 people who all live in that same zip code and all get their mail sent to that same zip code. But I can't say that one more is this much further. It's all jumbled up at this point, and all that they are is locators. This person belongs in this box, which is why they're qualitative variables. Similar things happen when you deal with phone numbers or when you deal with addresses. Really, if they're numbers without context in a mathematical scale, then they're qualitative, not quantitative. So completely understand if that was the one you got wrong, but number 5, hospital zip code, should be a qualitative variable. For number 6, the number of babies that a doctor has delivered, that's quantitative. I could have one doctor that in his career delivered 124 babies, another that delivered 85. I could set them up on a naturally occurring numerical scale. Type of medical insurance is qualitative. This person has Aetna, this person has Blue Cross Blue Shield. I can't really make comparisons between them, but I could say which one a patient belongs to. Finally, the cost of the hospital stay is quantitative. This hospital stay costs $780, that one costs $1,092. I can see which bill is higher based on looking at them and putting them on the naturally occurring numerical scale. So here are all those done out. Again, the real tricky one is this hospital zip code. Once we know whether something's qualitative or quantitative, when we decide qualitative, we can stop there and we don't really need to make a further distinction. But quantitative has two different types of quantitative variables. A discrete variable can only assume a finite or countable number of values, while a continuous variable can assume the infinitely many values corresponding to the points on a line interval. Again, these are book definitions. I just want you to understand how they work in context. If something is discrete, you cannot have parts of a whole. You either have something or you don't have it. So the examples here of discrete is number of people that are on a train. If a train is moving, there's either 100 people on it or there's 101. There's no possible way that 150 people can be sitting on that train. Similarly, how many stops the train makes. The train can stop to let people on and off, or it cannot stop. It can't make half a stop. So when you only have these whole number answers, that's a discrete variable, as opposed to a continuous variable. Continuous variable, you can have parts of a whole. So for instance, the time until the next train arrives. The next train could arrive in 10 minutes, could arrive in 9 minutes, 48 seconds. If I went to tenths of a second, I could do that. Basically, there's nothing that says it has to arrive exactly after 10 minutes or 15 minutes or some whole number. For that reason, it's a continuous variable. Similarly, the length of the train in feet does not have to be exactly 100 feet. It could be 100.125 feet. There's nothing saying that you can't have part of a foot in this context. That's why it's a continuous variable. So, I want you to think about these 6 quantitative variables and whether they would be discrete or continuous. Yeah, I'm going to give you like 20 seconds to think on your own. It's possible that you don't have background knowledge about NBA games. No worries. If that ever happens on a question in your homework, ask me about it. I'm going to send you back the knowledge that you would need to answer it. In this case, the variables are points scored in an NBA game, height of the tallest player on the court, time remaining when last shot is taken, number of referees on the court, fan attendance for one game, and the average per game attendance for the year. So when we talk about points scored in an NBA game, again, this might have required some background knowledge, but there's no way to score half a point. Free throw gets you 1 point, a regular field goal gets you 2 points, a 3-point field goal gets you 3 points. There's never a time where you can have half points. For that reason, this is a discrete variable. A team can win 123 to 110, they can't win 123.5 to 122.8. Second one, height of the tallest player on the court. If Joel Embiid's out there, he could be 7 foot, 2.19 inches or something. There's nothing that says he has to be exactly 7'2". So for that reason, heights are a continuous variable. Time remaining when the last shot is taken. Again, this might require some knowledge, but the clock in an NBA game does go to tenths of a second. So there could be 0.3 seconds remaining, and a team can inbound it and get a shot off. For that reason, I can have parts of a whole. This would be an example of a continuous variable. Number of referees on the court. I could have 3 referees, I could have 5, but there's no way to have 3.5 referees. Either the referee is on the court or the referee is not on the court. So the number of referees on the court is a discrete variable. Fan attendance for one game. If I'm going to a Manor basketball game, there could be 100 people in the stands, there could be 101, there can't be 100.5. Either somebody came to the game or they did not come to the game. I can't have a part of a fan of the game. That's why that would be a discrete random variable. But when I go to number 6 and take the average, if I look at the same situation, if one game has 100 fans, the next game has 101 fans, the average would be 100.5. When I'm looking at it as an average, that same variable becomes a continuous variable. even though it's the average of something discrete, making it an average turns it into something that can allow for parts of the whole. So here are all those answers put up, and that ends the first lesson. I recommend that you look at the classwork, try the problems on your own, and then look at the classwork video that goes over them. Here's just a little flowchart showing how we choose the path for the data. Either we choose that it's qualitative and stop there, or if we choose that it's quantitative, then we further decide whether it's quantitative discrete or quantitative continuous.